Alrighty, let's take a look at number 13 from 3.7 Webwork. This problem is very similar to number 12, except that in number 12, you had a fixed volume and you were trying to minimize the cost. And in number 13, we have a fixed cost and we're trying to maximize the volume. So it's like the opposite problem. Since we're trying to maximize the volume, we need to start with that equation. This is our objective function. Okay, and the volume of this thing is x squared times y because we have length times width times height. Our constraint is the cost, and that's given by these two parameters. We know that the cost is going to be $225, but we want to write the cost of the tank in terms of this 3 and this 2 to get our x's and our y's involved. So we know that the cost is going to be based on the cost of the sides plus the cost of the bottom. The reason that I can include all the sides together is because they're all the same shape. Do you see how they're all x times y? And there's 4 of them. So we're going to take the area of one of the sides, which is x times y, and we're going to multiply that area by the cost of the sides, which is $2 per square foot. So this is the cost of one side. And then we're going to multiply that by 4 because we have 4 of those sides. And then the area of the bottom is x squared, and the cost of the bottom is $3 per square foot. So our cost of $225 is going to be split up between 4 of the sides. If we simplify this, we get 8xy plus the cost of the bottom. And now from here, remember, we're trying to get rid of that y. We're trying to turn it into an x equation so we have a single variable equation. So we're going to need to solve for that y in the cost equation. So we get 225 minus 3x squared. That's equal to 8xy. We can go and divide that 8x. And we get that y is equal to 225 minus 3x squared divided by 8x. Now let's go ahead and plug that in to our volume equation, which will now be a function of x only. So if we take an x squared right there, and we're going to multiply that by 225 minus 3x squared all over 8x. And that's our volume in terms of x only. Now, of course, we're going to want to simplify things a little bit because that's going to make finding our derivative a little bit easier. So if we multiply that x squared through, one of those x's is going to divide with that x. And we're going to be left with 225x minus 3x cubed, all divided by 8. Another way to write this, we can split that fraction up if we want. We can write this as 225 over 8 times x minus 3/8 x cubed. Now when we take our derivative, we're going to use just our power rule here. We get 225 over 8 minus 9 over 8 x squared. So let's just pause really quickly and think about what we've done. So this equation right here is our single variable volume equation. And that's just in terms of x. And then we took the derivative because that's how we're going to find our critical point. Now to find our critical point, we want to set that derivative equal to 0. And we want to solve for x here. So we're going to do 9 over 8x squared equals 225 over 8. So we get that x squared equals 225 over 9, and we get that, of course, by multiplying by the reciprocal. And when we do that, those 8's cancel. We get 225 over 9. And so we're going to get x is equal to plus or minus the square root of 225 over 9. And we can count out the negative here because we're dealing with this box problem and we want our x dimension to be a positive number. We actually could have stipulated that at the beginning, all the way up here. We could have said that x is greater than 0 and y is greater than 0 as part of our domain because we're dealing with a real world problem. All right, so now we need to determine whether or not this critical value gives us a maximum or minimum because we want to find the absolute maximum of this thing. So we can go ahead and make our number line just start at 0 and go off to infinity there. Remember, we're doing a v prime number line here, so whenever we plug in stuff, we're going to be plugging into v prime. Our x value that we're worried about is square root of 225 over 9. Okay, and that's a little bit bigger than 1, obviously. And this number in here, that's like 200 over 10. That's like 20, maybe. So let's go ahead, but it's going to be a little bit bigger than 20, all right? So let's go ahead and plug it. I don't know. Let's say we plug in 40 there. And we're going to plug those into our derivative equation. Okay, so if we find v prime of 1, we get 225 over 8 minus 9 over 8. And that, of course, is a positive number. And if we find v prime of 40, we get 225 over 8 minus 9 over 8 times 1600. And that, of course, this is a really big negative number right here, so that's going to be a negative. So what we've shown here is that we have a local maximum. We can actually extend the reasoning here. This is, in fact, our absolute maximum because we've actually considered the entire domain here. And if it's increasing up to that local maximum and it's always decreasing after there can't actually be another maximum. So this local maximum also is the absolute maximum. All right, so we know that our critical value here at the square root of 225 over 9, that is a value of x that's going to maximize the volume. So our problem asked, what are the dimensions that we should choose to maximize the fish tank? And then also, what is the maximum volume? Okay, so we have two different answers here that we have to consider. We need to figure out the dimensions, and we need to figure out what is the max volume. Well, we already figured out one of our dimensions. We figured out that x is equal to the square root of 225 over 9. Okay, and that's actually going to be two of the dimensions, right? Because this is a three-dimensional prism. So two of the dimensions are both x, square root of 225 over 9, square root of 225 over 9. Should be a 5 there, not a 9. And now we need to figure out our y dimension, okay? Because this is x by y. Well, how do we find y? We can actually go back and we can use our y equation here. So we know that y is equal to 225 minus 3x squared all divided by 8x. And we can just plug our x value into there. And we don't actually need to simplify at all. So our y value is 225 minus 3 times the quantity square root of 225 over 9 squared divided by 8 times the quantity square root of 225 over 9. And that's going to be the dimensions that maximize the volume. Now, how do we find the actual maximum volume? Well, we can look back up to our volume function up here. We can even use our simplified one. And let's go ahead and plug our x value into that volume function. So our volume function, we're going to find the volume at the square root of 225 over 9. And our volume function is 225 over 8 times x. So 225 over 8 times the quantity square root of 225, keep writing 9 there, over 9 plus, oh, sorry, it's a minus 9/8 that x value cubed. And so again, our x value was 225 over 9. So in the Webwork, A is going to be your x value, B is going to be your y value, and C is going to be your maximum volume.